Hello there, calculus folks. Today I'm going to be talking to you about some stoof. Mainly we're going to look at some applications of differential equations. So we've been doing a bit with differential equations and solving them. So today we're going to be focused more on doing, using differential equations to do some stuff. My last example set I really don't like, so I'm not going to lie to you. Probably not going to ask you a whole lot of questions on it. But the middle examples, pretty great, not gonna lie. All right, so I thought I'd take a minute now that we have, two ways in which to solve things, separability and linear first order equations, and walk you through how can I tell, which one I can do. And, you know, that kind of stuff. I don't know how this is gonna go. We'll find out. Anyway, so what I'm going to do is we're going to say, hey, let's look at these differential equations. Let's see if I can separate it or write it as linear first order. So we're not going to be solving, we're just going to see, hey, can I do some of my solving methods to this? So this first one, we want to ask ourselves, I'm going to do separability first for all of these, just so you know. I'm going to ask myself, can I separate this? So can I move all the y's to one side and all the x's to the other? And this one only has y's in it, so I'm just going to take both sides and divide by these two terms. So you'll end up with 1 over y minus y over 500 times y dy equals 1.456. And then remember, for separation of variables, on one side you integrate with y, and on one side you integrate with x. So this one is separable. Let's see if I can write it as a linear first order. So to write it as a linear first order, I need to be able to have my linear first order y terms be added or subtracted to my dy dx, and then all my x stuff on the other side. So one of the problems with this one, and I'm going to write this over here, dy dx equals 1.456, and then I've got this stuff. So I'm going to multiply this out. So I'll get y minus y squared over 500. And this is right where you're going to have a problem. Since I don't have just y times something, I have a square present, a higher order than a first degree. I cannot do this. This is not something I can do with the integrating factor method. So not linear first order because of that second degree. So when it comes to finding a solution to this one, the only thing you could do is separation of variables, the thing I wrote first. Okay, let's take a look at this next one. So this next one is way more typical than the one I just wrote. It's actually far more common. So here we go. So I've got dA dx equal to 1.05a plus 1,000. So for separation, so my a is acting as my y, I can just divide both sides by this. And so I'll have 1 over 0.05a plus 1,000. That's 1,000, not 100. dA equal to, and I'm just separating the differential dx, and then I can integrate both sides. So this is separable, because I can collect all my variables to one side and all my stuff to the other. Now we got to ask ourselves, is it linear first order? So dA, so remember thinking a is our x guy, so I need to move all of my stuff with y on it to the other side, so I'm going to subtract 0.05a to both sides minus 0.05a equals 1,000, and this one is linear first order. So I've got a, which is acting as my y, times some function, that's going to be my integrating factor, it happens to be constant this time, equal to another side, which is supposed to be our x stuff, but there is no x stuff here. And it's fine to have this be constant. So at this point, we're good. This is linear first order. So, yeah, cool. So this one you could do either way. And you'll see me when we're doing some of our examples, I'm going to actually do ones like this because this one is super common. So I don't know, put little hearts and stars and stuff by it. You get a variety of different ways you can solve this one, and I'm going to do it one of each so you can see that, but they all look like this, a times a constant plus some constant. And they're pretty easy. I don't really have a preference for this one. I like doing it both ways. You're going to see me do it both ways for fun. I don't know, for math, which is fun. Ooh, this one already should be like, itching your skin a little, kind of thing. I'm going to square this, so that would be x squared y squared. So I have x dy dx equals x squared y squared, and then I'm just going to divide, ooh, that is not good, oops, divide both sides by x. So I'm trying to do separation of variables in case it was unclear. So I have dy dx equal to x y squared, and that's going to work because then I can just divide both sides by y squared, and that'll move my y's over and I'll just have x on this side. So that's good. So let's separate this. So I'll have the integral of 1 over y squared, which we'll probably do as just y to the negative 2 if we were integrating this, equals the integral of x dx. Check, check. This is super separable. And as far as linear first order, I could actually tell all the way back here that this wasn't going to work because y squared, not first order, can't be done. So I don't know, I haven't been using, so if this is check, then what's this? X? I don't like that. Let's go with like sad face. Either way. So to just summarize what we've seen so far, we've seen two that are separable only, one that's both, and then, this next one is something that you might recognize if you did some calculus involving biology back in the day. In particular, this is a temperature change differential equation. It's about, moving away from 300 degrees because that makes sense. Ovens get up to 300 degrees. This isn't too unreasonable anyway. This one is separable, so I can take this and divide it by t minus 300 on both sides. So here we'll have 1 over t minus 300 times dt, capital T, equals negative not 0.055, 0.55, little t, little dt. Integrate, this is definitely separable. If you're thinking to yourself, oh man, I'm not sure I remember how to integrate this, this is totally a candidate. Anytime you have 1 over something fairly linear looking, you should use u substitution, or I've been using w, so I would use w equals t minus 300. And then our differential for w, dw, would be the derivative of this stuff times dt, which would be just 1 dt. So this is separable and actually really easy to integrate. This one's fairly simple. Can we write it as a linear factor though? Let's try. I don't know if I'm sure what this one will do. When it comes to the integrating factor, I don't know if you've realized I've been doing this. Since it's all like plus plus plusy and like, what's a good word for that? Expanded. Anytime you see multiplication, you should go ahead and distribute that because that'll make it easier to arrange into a linear form. So I get negative 0.55t plus 300 times 0.55. No, I don't want this up. There we go. Sorry about that. Would be plus 165. I calculated that ahead of time. Equals dt. That's just fun to say. The big T over the little t. That sounds weird. So remember, t is behaving like our y, so I'm going to go ahead and move this term over and just leave that constant term on the other side. This looks a lot like our constant times a plus another constant. So this one hopefully looks just like that, and you see, oh, this is kind of the same thing, which means I totally can do the integrating factor on this. So yes, this is linear first order. So this is yet another one that's both. Woohoo! Let's move on to another one. Okay. I am just barely going to fit E in here. So this one, like, I immediately look at this and think, oh, let's try integrating factor on it because it looks fairly linear. dy dx, that looked weird. Minus 2x squared y plus 3x squared equals 0. So I'm actually going to do the linear first order first. So you want your stuff times y on this side, but you want your stuff that's not times y on the other side. So I'm going to move my just x by itself stuff over here, and that's fine. So here I'll have x dy dx minus 2x squared y equals negative 3x squared. And at this stage, remember you have to have dy dx by itself, so we're going to divide by x. Remember, whatever you divide one side by, you got to do the other side. So I'm just doing it equally across all my terms. So I get dy dx equals some function of x times y equals, well, some function of x, which is exactly what linear first order looks like. So this is linear first order. Let's see if I can separate this. Let's see if I can get my x's and y's apart. So similarly to what I did down here, I want to see if I can get dy dx by itself, because that's really the first step in separation. So I'm going to move these both over and divide by x. I'm running low on space, so I'm going to do that all in one step. Dy dx equals, see if I'm adding this over, this will be plus 2, and then dividing by an x gives me 1 less power of x. And this one will be plus 3, nope, not plus 3, minus 3. Ah, itchy. And then x squared divided by x will be just an x. Hopefully that wasn't too horrible for you. What I'm going to do now is I'm going to factor out an x, since they both have an x in common. So this will be 2y minus 3 equals dy dx. And then I'm just going to divide both sides by my y stuff to get my y's separated. I shall have more space for this one. So on the left-hand side, I'll have 1 over 2y minus 3 dy integrated equals just an x dx integrated. So it's separable. So this is yet another one that's both. So I'm hoping you notice that both is more common. Things that are just linear, like this guy, you can always adjust like this so that you can factor and divide, which is kind of nice, because your y term, if it shows up in the linear version, the first order linear guy, you know, it's going to only show up once. So that means you're going to be easily able to separate it from the rest of them. I'm hoping you're seeing that. So if you can do it linear first order, you can usually do it using separation. I shouldn't say usually, like 90% of the time. And that's where we're at. So hopefully recognizing what you should try first is helpful. I usually will try separation of variables first, and then if it doesn't work, try linear first order. There's a reason we teach them in the order that we teach them, and that's because that's the order you should do it in. Are you ready? Moving on. Continuous deposits. So this is a rather interesting, what's the word? Concept. So this goes along with that common equation I was talking to you about. So suppose we have an amount A earning compound continuous interest at the rate R. Little r. My r's always end up looking like b's. Okay. Over time t. Now, if that was the only thing that was happening, then we would say the change in the amount of interest that I earn over time, because that's what differentials are, would just be the rate times the amount I had in there. Got it? But we also want to do a regular deposit. So this is what a savings account would do if you took your, biweekly or monthly paycheck and always deposited like $100 in there to build up your savings. It's exactly what's happening. If D, capital D, is a regular, so when I say regular, I mean like it deposits every time unit. So T, if it's in months, it must be in months. Into the account. It'll also earn interest. So then we'll just add on D. So the rate of change of the amount in your account will be, I'll earn interest on the amount that was there previously, plus I'll add the deposit. So as this runs over time, the deposit will add in and become a part of the amount. But it doesn't earn interest when it's first thrown in there. Cool. Now what I want you to show you is how to solve this. You ready? Hopefully this looks familiar as far as separation goes. I literally just did one just like it. So what I'm going to do is I'm going to divide by R A plus D. So 1 over R A plus D on one side equals, well, if I take this and divide it by itself, I just have a 1. And then I'm going to separate, so I'm doing dt on one side and dA on the other. Be careful, A is my variable. Integrate, integrate. And now I'm going to need to do some substitutions. I'm going to use a different color because I like to change my colors when I substitute. So I'm going to use W equals RA plus D. Remember, R and A are going to be values. So R, if it's a rate, might be like 4% or 5% or 3%. D is like, say you deposit $100, it's like 100. So then DW, when I do this differential and derive with respect to A, I'll just get a R dA. And because it's a differential, I get a dA, and divide by r on both sides. So I want you to think of, okay, I'm going to replace this integral with what it's equal to. It's going to be 1 over w with a 1 over r. Oops. Integral 1 over w dw. My equal signs are not fitting well. I'm going to go ahead and integrate this. So the integral of 1 is just the variable itself, which is t, plus some constant c. Hopefully this is feeling a little bit like, well, last week. Anyway, so now I'm going to multiply both sides by r. So just to get that r out of the way. Or do I want to do that later? Let's do that later. Let's integrate. So 1 over r, hopefully you remember the 1 over function is always just the natural log. When you integrate it, I could write another plus c, but you could just add it over with the other c. There's no point in this. So now I'm going to multiply both sides by r. Woohoo. So here I'll have the natural log of, remind yourself what w is equal to, rt, and c is a constant, so really r times c is just some new constant. I don't know if you really want to give it a new name. So, and I can't use a, so I don't know, I'm just going to keep calling it c. So at this point I need to exponentiate both sides to get rid of that natural log. Let's go up over here with this. So these two will cancel, and I'll end up with ra plus d equals e to the rt, and I'm going to pull that move we usually do where I pull a constant out front, but I'm going to call it b this time because a is already in use. So we're going to let b equal e to the c, because remember, addition inside the exponent is the same as multiplication outside of the exponent with the same base. So then I just got to divide by r and add d, or sorry, subtract d. So b over r e to the rt plus, or not plus, minus d over r. I did that kind of fast. So that's what our general solution will look like. So if you're wondering, how am I going to figure out what these constants are, like b and d, you're going to have some idea what your initial deposit is, and we're going to do that in this next one. So you'll be able to use that to figure out what your constants are. So you'll know what d is, you'll know what r is, and then you'll be able to solve for b, because you have to have something in your account in order to open it. Here we go. Let's look at an IRA, which is a pretty typical retirement account. So we have an initial deposit, which means the amount when I first open the account, so times 0, is $3,000. So I'm just summarizing this. And the IRA earns 4%, so my R is going to be 0.04. And then continuous deposits are made 1,000 per year, so my D is 1,000. And we want to figure out the accumulated balance after the end of 15 years. So we're going to deposit $1,000 into this account for the next 15 years, compound continuously. So what I'm going to do now is I'm going to set up the differential equation. So dA dt is equal to 0.04 a plus 1,000. Oops, I want to do 100 instead of 1,000. That looks like Pac-Man. So at this point, since I have the general solution up above this, I could just use the general solution to write the answer to this, but I don't want to do that. I want to take you through the steps with some numbers, just in case that symbolic tomfoolery up above drove you crazy. So we're going to solve this using some actual values. So I'm going to do the same thing I did before. I'm going to divide all of this to the other side. Remember, when you divide something by itself, you get 1. So on the left-hand side, I'm going to get 0.04 a plus 1,000 dA equals 1 dt. I'm using my separation of variables. I got them separate. Going to integrate. I'm going to need to change my variable type. Let's do this weird raspberry color. That's cute. So my W here is going to be 0.04 a plus 1,000. Just barely going to fit it in right here. Yeah, make it work. dW will be 0.04 dA. So then we'll divide by 0.04. And you'll watch, you might have the instincts to figure out what like 1.04 is, and it's 25. That's fine. We'll use it later. And actually, you don't need to. So I'm just going to write it as 1.04. And my dA 0.04, pulled it out front, dW. Made that too big, 1 over W. equals t plus c. Woohoo! Don't know what c is yet, but I'm not done integrating. So 1 over 0.04 natural log of w equals t plus c. So at this stage, I'm going to multiply by 0.04 to get it to the other side. This is what I was talking about. C times 0.04 is just going to be some new constant. So if you want to call it something new, you can. On this side, I'm going to be just left with the natural log of, I'm going to remind myself what W it is, 0.04a plus 1,000. That looks kind of tiny. Let me rewrite that. I don't know, K. So here I'm going to have C, K be 0.04 times C. There, I fixed it. So now you have a new value because, you know, whatever. Same trick, we're going to exponential both sides. So I'm going to go up here. I wanted to leave space to write the solution, so it's not going to happen. Give it up. So 0.04 a plus 1,000 equals e to the 0.04 t. And I would have the plus k here, but then we can rewrite this as times e to the k, which I'm just going to call, I can't call it a, I already used c. I'm going to use b like I did up above. Why did I pick k? So at this point, then we just need to do some rearranging. So I'm going to add 1,000, divide by 0.04, yada, well, not add 1,000, subtract 1,000. So what's a? It's b e to the 0.04 t minus 1,000 divided by 0.04. Good times. Okay, at this stage, I don't know what b is. Hopefully that's the only thing you notice is missing, because at the end, I want to see what's happening after 15 years. I want to plug 15 in for time. So at this stage, I'm going to be using that initial value to figure out what b is going to be. So 3,000 is equal to b e to the, well, I'm putting 0 in for t, so that's just 0. So this is just a 1 minus 1,000 over 0.04. So now we're just going to solve for b. So I'm going to multiply both sides by 0.04 and then add 1,000. So if you take that 3,000, multiply it by 0.04, you get 120. And then you add 1,000, so you get that b is 1120. So to rewrite this, I'm going to make this look much nicer. So a is 1120 e to the 0.04 t minus 1,000 over 0.04. So what I want to do is I want to take both these and divide them by 0.04 so this hopefully looks nicer. So that'll be 28,000 e to the 0.04 t. Oops, I erased my t on accident. Minus gets 25,000. Yep. I'm calculating as I go. That's my A. A. Okay, still not done. The last thing I need to do is figure out how much is in here after 15 years. This is the most boring part. So 28,000 e to the 0.04, 15 minus 25,000. When you calculate that, you get $26,119.33, which isn't too bad. So remember, this was doing an annual deposit, so just once a year putting in some money. You can imagine that if this was something like compound monthly, that would be a much faster growing account than this would be. Does that make sense? Because it's also like, you know, you're only putting in money once a year. That's not good. You want to do more than that. Okay, let's do another one. So this one's very similar, but it's slightly different. So this is like what you will do after you're done working and you've finished up with all of your stuff and you're retiring. And what you want to do is you want to draw payments on your retirement account every single month or every single year. Okay? So suppose your retirement account is only $10,000. So maybe this is a place you worked at for a little while, but then you left and went somewhere else. So, you know, you only have a little bit in that account. And then you're going to do continuous withdrawals at the rate of only $2,000 per year. I know everything's annually here. It still works monthly. It's just that, you know, when you're dividing out your rate, you got to divide by the number of compounds and blah, blah, blah. Or you just make your time monthly for everything and you just have to adjust your rate and stuff. Anyway, So what I want to do is I want to write the differential equation that describes this. So initially, at time 0, when we start withdrawing, we have $10,000 in this account. And then, every year, I'm still earning interest on the account, so I get that 0.12 times the amount that's left in the account. But I'm also losing money, so I'm taking out $21,000 a year. Sorry, $2,100 a year. So it's negative here because you're withdrawing. Withdraw. There we go. All right, so let's do this. So for this differential equation, I'm actually going to solve by using the integrating factor method just to give you the other way to do this. So I'm going to set it up so that it's a linear. So I need dA dt with my stuff with my my dependent variable over here. So I need to subtract over the 0.12a equals negative 2100. So now I need my integrating factor, my I. It's just my stuff times a integrated dt, because that's my dependent. Here we go. So this will be e to the negative 0.12t when you get done integrating it. Remember, no plus c when you're doing the integrating factor. So I'm going to take everybody and multiply by I. This is where things get weird. Yay! So I end up with e to the negative 0.12t dA dt. Remember, that's just going to make my big D, sorry. Negative 0.12 e to the negative 0.12 ta. And this makes sense because remember, when you derive an exponential, you end up with deriving the chain, which would give you this. And anyway, hopefully that looks like what you're expecting. Negative 2100 e to the negative 0.12 t. So at this point, I need to use my big D notation to write this as a derivative and then integrate it. That t doesn't look like anything. So this would be big D with respect to t, not x, because that's what I'm deriving with. E to the negative 0.12 t a. Remember, it's always your integrating function a times your independent variable, so that would just be a. I'm going to integrate that with respect to t. Remember, with this one, you integrate with respect to the same variable, unlike separation of variables, where you're doing different variables on each side due to the separation. Okay. Whew. I am going to run out of space with this one. I can just feel it coming. So I'm going to steal some space from B and C probably, because B is just like, oh, put in 2. You know, it's boring. Anyway, so you integrate this one. Integrals undo derivatives, so this is just going to be e to the negative 0.12t times, oh god, my t's are getting so small, times a equals, now we got to integrate this. So hopefully you remember, when I integrate e to a constant, which we usually called a, times a variable, we end up with e to that stuff divided by 1 over the constant. So, or sorry, divided by the constant. So here I'm just going to get negative 2100 over negative 0.12 e to the negative 0.12 t. Don't forget your waitress, got to have that constant. Okay, this is looking rough, real rough. But at this stage I want to get rid of the stuff times a. These are some pretty pastels, but will never show up, so let's use bluish, kinda. Indigo. Ooh, do you know where to go? Indigo. Let's divide by e to the negative 0.12t. Hopefully you're seeing that this one has that in it as well, so that's going to make this just a constant. Here we go. So over here I'll get a. Here I'm going to get some cancellation, and I'm going to calculate this, which comes out 17,500 things. Well, this is money. Monies! Plus c times, okay, negative exponent, I can make it positive by moving it into the numerator. Woohoo! Cool. Now all I have to do is solve for c, which I'm going to try to fit right here. We'll see how that happens. So remember, the initial value in my account is $10,000. Plus c e to the 0, because we're putting in times 0, so I'm using that a of 0 was 10,000. That initial deposit. So this is just going to be a 1. So to find c, I'm just going to subtract this. Oh, this was easier than I thought it was going to be. Yeah, you know what? I think setup for integrating factor is kind of terrible, but at the same time, like, actually, this was a little easier. Oops. So using that, my final version of the equation is that A is 17500 minus 75,000, sorry, 7,500. I do not do my hundreds and thousands right. 0.12t. Good. Let's use that. So how much is left after 2 years? These are dumb. Put it in 2 for t. Let's see how much money's. $7,965.63. That's kind of fun. So after 2 years, the account's depleting, but that's okay. That's what it's supposed to have happened. It was $10,000, now it's less. That's exactly what we want to see. When will the account actually be depleted, as in there's nothing left in it? So this is asking when is the amount zero. So to set this up, you do 0 equal to the 17,500, almost said 1750, minus 75,000 e to the 0.12t. So at this stage, I'm going to subtract 17,500, then divide by 75,000. I wrote this initial part too big, and now I'm going to run out of space. But the algebra part is important. Okay, so yeah, this, when you reduce it, will be 7/3. And now I need to get to an exponent. Hopefully you remember the easiest way to do that is to log both sides. So I'm going to do the natural log of 7/3 equals the natural log of e to the 0.12t. Since logs and exponentials are opposites of each other, they're inverses of each other, these undo each other, and you just get 0.12t. Let's go up over here. So my time is going to be the natural log of 7/3 divided by 0.12. When you do that, you get 7.0605. So you will get 7 payments, and then that last payment, the 8th payment, will be less money than what you expected. It won't be that 22,100. It'll be less. So on the 8th payment, it'll be less, but it'll be after the 7th payment. Oh, after the 8th payment, you won't have any more. So this only lasts 8 years. And the 8th payment's less. So this is not a great annuity because it's only going to last you 8 years. Da 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 da. So this next part is going to be about epidemics and rumors, and I have already decided that I am going to cut this material, so this is going to show up on your note sheet. I don't think that this is something timely or that something we should be talking about in the times that we currently live in. It's also not something you're ever going to use as people interested in economics and economic recovery. I don't think that this is going to be something useful for you. If you would like to see this part of the notes, I'm not going to ask you any questions on it in the homework. Feel free to request it, and I will make a separate video on this. That's all I have for you today, because it's also been like 40 minutes.